Hello everyone, thank you for coming today, and I hope you are all enjoying DevOps as much as I'm enjoying it. And so today we are going to speak about signals from the deep web. It's going to be a very long presentation starting from the Big Bang to, to today, and then we're going to have time for questions and answers and also for a demo in the 15 minutes. I'm going to start speaking a little bit about the company I work for, which is Anaplan. Not sure if many of you have heard about Anaplan. We are in the space of the connected planning. We are quite big now with over 1,100 customers, most of them placed on the top 1,000 big companies. We have 175 partners. We are present in more than 40 countries. We are growing really fast. I joined the company sometime November last year, and the number of employees were at about 900. We are closer to 1,500 now. We have an app hub with more than 230 apps, and then we have more than 20 offices around the world. Just a few words about what we do. I'm going to... Sorry, the slide. So I'm just going to present the problem that we deal with as something that you probably all can relate to. At least myself, I've been working for the last 5 years at least trying to solve a problem where the business users love Excel and try to do everything in Excel, but they want their data to scale and to be shared and to be easy to navigate to. So they want a database and a single source of truth. And then they want their data also to be explored via reports and to be meaningful and to look at dashboards, and that's why. And they want all of this to be in real time, and that's why very often you put a business intelligence layer on top, and then present the solution to your business users. But they still love Excel, so go back to Excel. So that's a continuous loop circle, and that's where Anaplan has placed themselves by creating this SaaS platform. That does exactly that. So you have all the flexibility, the same as working with Excel, but the data is actually, first of all in memory, and it's very fastly updated and has all the features of a all-up a database. So, and business users tend to do what they love doing, but they have all the features of all of that solution that we were presenting early on. So, and how we do that? First of all, the platform was born cloud native, is multi-cloud. We have a patented technology, which is the hyperblock, which actually brings all of this together, and we use all the modern architecture technologies, so container-based, event-driven, and you can see some of the tools that we use. And where we're heading to, the next generation platform is looking to scale even more with removing any size limit on our models, and we are building a top-level infrastructure to support all of that. But moreover, we're investing more and more in machine learning capabilities and ideally becoming machine learning native, the same as we were cloud native. And that is where this presentation places us all today. So at Anaplan, as employees and based on our interest, we get the chance to actually participate to research projects with different universities. And myself, I'm participating in a research project at Birkbeck University of London, where we're dealing with some of these problems, and that is more or less the agenda, what we're going to look at today. We're going to speak a little bit about the deep web and the challenges that it presents and why there is an interest on the data in the deep web. We're going to show an implementation of a distributed scalable architecture for mining web data from the deep web with all the challenges that it presents. we're going to look at a particular case of the features that the deep web presents, and that is ephemerality and anonymity, and how we can actually get this data and make sense of it. And at the end, we're going to see of how we can use this data and what we can actually deduct from the data that we've extracted. And then we're going to have a live demo of how actually to run a campaign of extracting the data, how to actually use this data, and then we'll have also time for questions and answers. Just 2 words about me. So I have this dual life, academic and professional, and also I have spare time for family. As I said, I joined Anaplan recently, and I've been working as an engineering manager in the past 5 years or so, and I have about 15 years of experience in the software engineering space, and also a PhD candidate, and my research context is trying to build a scoring model, a trust scoring model based on your social network activities. I know that it has been done in China now, but it's something similar. And there is a few papers that were presented recently, and there are a few other papers that are upcoming next. One is at the WebSci in Amsterdam, and another one in Zurich at the computational social science in September. So let's come to today's presentation. So very often we see this pattern where most of the research projects or companies tend to use data coming from the web, from the mainstream web, and this data mostly is coming as an API. So all of the conventional websites that we know of tend to present an API. Sometimes it's free, sometimes you pay for it, but that's how you usually get the data. Many other businesses have their business model built around actually scrapping this data. So if you think of Skyscanner or other aggregators that go on the web, try to get the data, and then you do your search and they present you with the results. That's more or less what they do. However, this has been shown to not be very reliable, especially when you're doing research and you're presenting results to the scientific world that might be based on biased API. In this paper discussed by Jürgen Pfeffer in 2018, he showed how the sampling API that Twitter uses is their streaming API that when you go and try to get data from Twitter, that can be actually manipulated to input into what data is presented into the API based on what you wanted to present. So the experiment that they did was to actually synchronize with the sampling mechanism, and they managed to have their tweets appear 84% more often than with the amount of time that they were posting for. So just to explain a little bit, so every time you tweet, your tweet will get a tweet ID. The tweet ID is coded in this method using this mechanism, so it's a 64-bit of which the timestamp is the main part of it, and then there is a data center, work through it, and other numbers. However, the sampling API will use the timestamp to show this data. The sampling API only presents to you with 1% of the data, so that you have 1% of the tweets that hit Twitter, apart from some academic institutions that get about 10%. So these 3 last numbers is what so the sampling API will present to you. So based on the 3 last numbers. So what they did in this experiment was that they set up a few bots, and they managed, by doing some experiments, to actually sync the bots to only post at the bits that were selected by the sample. So they managed to input at exact certain time a certain topics. Actually, there is the tweet, and then that tweet will appear in the results of the API very often. So if someone was doing some research on this data and will look at what was coming up, they would think that somebody is talking about whatever the topic was here, say 84% more than that in reality was happening.
So it's 84% or 84 times?
Is 84 times, sorry. 84 times more likely to get picked. So that is actually a massive result and can influence can invalidate actually a lot of research papers that have been presented in recent years. And so that is a public API, so somebody that is willingly wanting to give you the data. Now think of all the cases where actually you are trying to scrap data and use this data differently. And even more when we're talking about the deep web. So just to clarify a few definitions, what we mean by deep web is content that is difficult to scrap or actually does not appear in the normal search engine. So if you go to Google, it's very unlikely you'll get results from the deep web by definition. And as part of that also there is the dark web, which is the part of the web that is hidden behind proxies and so like Tor. That also is so the two are not the same thing. However, dark web is part of the deep web. And now, can we trust the deep web APIs? That's a very good question, because most of the time they will not have an API. So that's where the challenge comes. So that is where, first of all, why we think that the deep web is important. So why should we care about the deep web? First of all, 96% of the World Wide Web belongs to the deep web. So what we see on Google when we do our researches, we are actually only seeing 4% of what there exists. So it is actually quite important. But not only that, if we look at the recent year papers, so we can see that the deep web is being used more and more as an alternative source of information. And that has an impact actually on everyday's life. If you think of all what is happening in recent days, won't go into political details now. In another research by Stringini in 2017, we've seen that actually people that participate in communities in the deep web are coming together and intentionally are doing raids toward the mainstream media. So they get organized around a certain topic and they actually are bringing this topic into the mainstream media intentionally. So, and that influences communities because you might think that there is a certain pattern in the way people are thinking. And there is also a lot of other reasons that we've seen in recent publications. So disinformation welfare, state-sponsored trolls, alt-right echo chambers, and there is a lot more that is happening there. So the deep web is actually subject of a lot of studies in recent years. We've seen it happening with a lot of publication, and there is also the event of the computational social sciences that is getting more and more attention. So what is the challenge? Obviously the challenge is around the fact that it is non-trivial task to retrieve usable information from the deep web. That is, by definition, they try to hide this information. They don't want you to see because of their characteristics. So getting this information is going to be challenging, and some of the other characteristics that they have. So that is why we built a scrapping, so data mining architecture, so that it could be used around scrapping the information from the deep web. And this architecture have all the characteristics that you'll see usually on a web crawling, any web crawling engine. So that is, the system needs to be scalable, it has distributed characteristics and is multi-purpose, so you want it to go anywhere and to get you the data. However, we wanted this information to, this web scrapping engine to be used by the wider science community. So we didn't want it to be tied to any particular language. We want actually to be queryable. So we built on top of it we built it around a querying language so that you can write your query and then that query can be used to actually scrap the information. And that information needs to come out as semi-structured. So we want your information to be useful to you. We're not going and getting the HTML content that is not that is information that is difficult to use. We want your information to be actually semi-structured. When we say semi-structured, there is a certain structure and entities. is semi-structured because you will, so similar to what you see in the DocumentDB type of databases where the structure is actually not fixed, so it might change. And it is multi-tenant. That was a necessity for it to be multi-tenant because different people will have different interests, and actually they will have different perspectives even to the same website, to the same data. So what did we use for the querying language? So I want to speak a little bit about Vadalog, which is quite a exciting involvement in recent years. Was presented last year by George Gottlob and his team at Oxford University. They built this framework that brings together all the tools that you might need to do machine learning. And ideally, when you write in Vadalog, you can write all the necessary constructs to be able to do it from start to end, i.e. from getting the data, from cleaning the data, from building and training your model, from presenting an output out of it, from interacting with APIs and building meaningful charts and dashboards. So if we look at this, that brings it all together. And as part of the data log, we can see oXpath. And oXpath is used as the web extraction tool. So in a framework, when you're trying to bring all the things together, you want the web to be your data source. And that is why oXpath is used in this framework for that. oXpath is actually a tool that is open source, so anyone can use it. And there is a lot of material around to be able to easily get to see how it works and build queries around it. And it is, as can be deducted by the name, is built on top of XPath. So XPath is the language to be able to explore any XML-like type of documents, which is what HTML is. And then oXpath adds events on top of it to be able to actually follow navigation and to be able to extract data into certain structures. So that is what oXpath is. So we took, this is what Vadalog language looks like, a Vadalog query. So input article is a Vadalog construct, qbind is a Vadalog construct, and then we're binding the article input to the now oXpath language, and this bit here is what you write in oXpath as a query. And that what this is doing is telling to Vadalog to consider the article as an input, and that input is coming from this web page, and you can see it in the doc, and then the data, and that's how you get to the data, and that is what that attribute is tagged at. So you can actually access this data in your further queries and analysis simply as attributes. So that's your article, and then we can see others. That's your author and title and so forth. So we build this architecture around oXpath, and as in any crawling, web crawling or data mining or web data mining architecture, you tend to have two type of extractions. You usually go on the web and discover all your sources. So that is what so you have this discovery query. So that is your research. You want to know. You want to have a full list of where your information is. So that's where you do your queries. You can follow, for example, a Google search, or if you are on Amazon, you follow a product search, and you have a list of all your products, and that is somehow your discovery. That's what you tend to write your discovery query towards. Then you run a discovery instance. Using that query, you extract all the URLs that you need. That will be your source of information, and you put it into a source storage. And then you have the extraction instances, again, using an oXpath query to define certain entities that will be extracted from all these endpoints that you discovered early on. So that is typical. So every web scraping architecture will look something like that. Then on top of that, we wanted it, as I said, to be multi-tenant and for you to have the possibility to run multiple projects. So at some point you might want to scrap, say, Amazon, and another one eBay, and then you collecting all this data. So each one of them is defined as projects, and then multi-tenant because different research entities or different people have different interests, so all of them will be able to use the platform and be isolated from and not influence each other. And then we wanted, obviously, all this to be scalable because some of the researches could be really intensive and long, and you want to be able to actually throw infrastructure at it and parallelize as much as possible so that they will go and get the information as soon as possible for you. And then on top of that, so we made this as all part of a container, and then obviously you want to add some orchestration around it so that you can scale as easy as possible. And then to add a few implementation details around it. First of all, I forgot to mention the fact that the moment you go at scale, you also need somehow a synchronization mechanism because you are having now multiple instances trying to do the same thing, so you need a scheduler, you need some synchronization. And we managed to get away without needing a consensus mechanism because of the type of data that we're dealing with. It's not so important if two instances at some point in a conflict end up elaborating the same URL. However, we have a distributed lock manager that actually manages the lock, which means that a certain URL that is being scrapped shouldn't go and be extracted by another instance that wants to go and extract data. Because of the implementation details, that might happen, but then that is fine with us because the second one will override the first one, will be more accurate, and that is okay, as long as it doesn't happen very often. The only reason why it happens is because in the implementation detail, we selected Mongo as our distributed database, and Mongo tends not to be consistent, which means that you might hit a query that hasn't been updated yet, which means that our reads are not automatic, which means that we might have the conflict. But other than that, the mechanism actually works pretty well. We've implemented the various discovery and extraction instances in Python. We use Docker for containers. We use Kubernetes for orchestration, and that is the web extraction architecture. So that is all in place, currently running on multiple projects, and that's what we used in the rest of the what we're going to go the rest of the presentation. What we use to extract the data. Any questions so far? All. Okay, good, thank you. So now we're going to go into more detail into one. We're going to select one of these deep web communities where we're going to extract the data and look at the characteristics and what the challenge that we're dealing with and how we can use this platform to extract the data. So in a paper published in 2011 where there was a detailed analysis of how 4chan works. Anyone heard of 4chan? Quite a few, good. So 4chan has been controversial for years now because of some of the papers that we presented earlier, because of, for example, if you think of Anonymous was actually born there, and because of raids that they tend to do to actually mainstream medias. So in an analysis that was done to 4chan, it was discovered that typically the median life of a thread is 3.9 minutes. So the way 4chan works is that, for example, if we take the political board, they have a certain number of threads that will be active at a certain time, and this number is 200, which means that if you post something, it will be in a queue until there is a space for it to go live. Then once it is live, if there is activity on your thread, which means posts, so people are posting and commenting around it, then your thread is bumped up. Otherwise, it tends to go down and other threads are posted. And then once it reaches the bottom, it will just disappear, deleted, forever, gone. You never see it anymore. So as you can see, information is recycled very fast. Things that go there might disappear forever, and no one will know. And if you look at the amount of activity there is, so if you post something, you would expect usually, well, that's not the mean, it's the median, because of it's a power law, the timing, so the mean doesn't make a lot of sense, but you'd expect about 3.9 minutes the life of a certain post. So that is very fast. And there is some more details. So if we think of the fastest one to disappear, 28 seconds. So you post something and you want to go and see it, and it's gone. So that's how fast that was. And then the longest one it took about 6.2 hours. So that is a massive time if you think of in 4chan time, especially because of the amount of comments that would have generated. So for it to be coming up on top for 6.2 hours, it means that it would have had a long list of comments around it. So what we want to do is actually to be able to capture all of that data. So we want to capture every single thread that is posted, not only, but we know that posts are being deleted. So not only threads, but once posts come to a thread, we can see by the activities, by monitoring, that actually at some point post gets deleted, and they get deleted very fast, so within seconds. So we want actually to capture all that data as well. So that is actually a difficult task. So especially to come up with what is the time. So how often you need to go to the site to crawl for data to be able to see all of that. And so this is a typical lifetime of a thread and how it happens. So this is the 200 threads. A new thread gets posted, gets to the top. Time goes T1. The thread is coming down already and has seen only 5 posts. So the activity is more or less okay. Then we can see the number of activity going, 25 posts. It still goes down because others are coming. And then we can see that at some point, we can see at time Tx, 25 posts. At time Ty, after Tx, 20 posts. So 5 posts actually got deleted. And we want to see that. And then going further, we can see a hyperactivity. The post got bumps up. It had actually 200 posts. And then it cools down again until reach the bottoms. There is a bit of an inactivity. Tn plus 1, the post is gone forever. And that is a continuous cycle. So the first challenge is, what is the time interval that you need to go to the web so that you can capture all of the activities? So if you think of, if you are somewhere here, so if you're crawling here and here, then you're missing things. You might not see. So you've seen maybe the 5 posts, but when you come here, you've never seen the 5 posts that have been deleted. And that also is a challenging task. We based our decision on this paper, the Adaptive Web Crawling by Provetti in 2008. And that is where we go next. This is a bit of a oXpath queries that we wrote to extract all this data. So the simple one, the discovery query, just go to the catalog and look at all of the live posts and give me the URLs. And then go to each one of the URL and start extracting the data. I want this information, and there is a lot together with the posts. So that's how you actually write the oXpath. So that's all why you need to use the architecture that we built earlier. And that is what you get as a result. So again, JSON is a MongoDB, as you all know, is a document DB, which means the data is stored in this format. This is just a small extract, but you can see message, date and time. It took me time to get a message that wasn't offensive or anything in 4chan, so that's quite neutral. So you have post number, author, and if you read one of these papers, about 96% of the authors are always anonymous. No one cares. And actually 4chan is completely anonymous. There is no registration. You post something, you are assigned an author ID that is only valid on that thread. If you post somewhere else, you'll have another author ID, and that is a random number. There is no way to identify anyone. You can give yourself an author name if you want to, but by default, everyone is anonymous. And that is the author ID and what it looks like. There have been quite a few, at this point, failed research to try to de-anonymize 4chan and try to make sense of the randomizing algorithm and see if there is a way to identify anyone who's posting. So far, no success. Usually, it is an image board, so you'll have some image URL, and then you start having replies, and then that is the cycle of data. So on top of that data, you start doing some map reduce, and you start bringing this data into some more meaningful information that you can use in your as input to your then analysis. But more or less, what we want to do out of this data is we want to look at all the posts, and we want to divide them in this format, because that's what we see mostly. So we have a format when on the last at the final state it looks like this. So thread 99 had 350 posts, or 350 replies, and that is the last extraction. So at the time of death, it looked like that. Now, if we look at all the history, we can see that from these 350 posts, actually, there had been posts previously that had been deleted. And we can see that on average, about 5% of the replies of the posts get deleted. So we extract all the deleted posts into another pot, and we look at also this data. And then we also build a cumulative data set with everything that there was. And this is going to be the basis for our analysis. So what we want to analyze is there a difference, or why are these posts being deleted? Especially considering that, well, actually not deleted, retracted, because we don't know what is happening. But considering that 4chan is pretty open, you can post pretty much anything. However, the number of deleted posts is quite high. So we want to analyze and see the content of what is being deleted. Can we make any sense of it? So we started with doing topic modeling on this, and this is more or less, so we used R to do topic modeling, and the library is available in R, and that is what is available in terms of libraries and the paths that you can take to take your information, build a corpus object, and do your analysis. Well, build a document term matrix and use LDA topic models, and then have these final topics, and then see if you can make any sense of it. That goes into quite. We're here talking about a lot of. Bias and inference, and latent directlet allocation, and then the other type of sampling, so the variational exceptional maximization. I can't even spell the one. It's quite complex mathematical models for ways on how to build the topic models. So the topic modeling at the end is a conditional probability analysis. So you take a certain corpus and look at all the phrases in there and see if you have, say, text A and B, what is the most probable next text. So, and that's how you build the phrases, the topics. And that is a machine learning topic, because to be able to get the bias probabilities, actually you train a model based on the most common phrases, and then that's how you know what will come next in all this. So at some point in time we did this, and that is as a result. These are the top 5 topics that we can see. I couldn't post everything, but this is the clean result. The clean result is the end result without the deleted posts. And the red dots are words that not for presentation. So that is, I mean, if you look at this, you kind of can make sense of what they're trying to speak about, or what that topic would have been at that point in time. They more or less fell in what 4chan political board is all about, especially if you take the red dots. However, it's still not telling us much. So what we went on to do next was we wanted to do sentiment analysis on this. So how many of these topics are positive by nature, or at least influence the whole extraction to be positive content, and how many of them are actually affecting it in a negative way. The reason we follow this path is because we wanted actually to do a comparison between what is the sentiment analysis of the residual, of the final extraction, what is the sentiment analysis of what got deleted, And what is the sentiment analysis of everything, so if they were together? So we wanted to see if we could make sense of this. Now, we did this a couple of times, and as humans, if we compare the results, it's difficult to see a pattern or a difference. So we could see that it tended to be more negative, the residual, than the initial, but that might also have been our intention. So it's not an affirmation that you can do easily. So what we went on to do next was to actually apply a Kolmogorov-Smirnov test, which is a signal test and is a comparison between two signals to see if these signals are similar, or there is a similarity, or they follow the same pattern. So what we went on to do is, if we take the residual sentiment, if we take the final post-sentiment analysis and then convert it to a certain signal. So we apply some normalization, and we want that to be actually, say, a sigmoid. That is the signal we want to get that data into. Then we apply the same normalization to the combined data. So what would have been the final state of the data if no posts were deleted? And then we go on to compare the two. So how do they look? I mean, are they look-alike? Is there a similarity? And obviously there is similarity. They follow a certain, they come more or less from the same data. However, what we came up with is that we can see a pattern that there tend to be, so the signal pattern tend to actually say that the negative sentiment tends to grow on the residual one. So the sentiment, the negative sentiment would have been less on the combined corpora. So that is, we're still actually analyzing this. It's not final, so you want to see that from different perspective, and the same test might not have universal validity. So that's where our current work is focused. And that is part of what we are going to present in September in Zurich, and that is, again, as I said, all ongoing work. But that is more or less where our research has brought us to. So to bring this all together, we started with Anaplan and all the challenges that we deal with in the world of today, and as such, we continue our research and all participate with research communities and to push our knowledge into the boundaries of where the current research is. And we've participated in this project. We dealt with quite a few challenges, trying to extract information from very challenging websites, and then making sense of this data into this specific case. That is all for today. Before me going into running a few demos, which will be around trying to run A-scrapping or looking at the data or see how what the analysis mechanism that we used, I don't know if there are any questions at this point.
So
yeah.
When you do the 4chan scraping,
yes.
At what rate do you scrape?
I'll show it now. It's 6 seconds.
Sorry?
6 seconds. It's variable actually. That's why what Provetti argued in his paper is that the more efficient way to scrap a website is to actually come up with a variable way, and they actually propose a formula to use. And the variable way is that you want to see actually at the rate of activities. When the rate of activity coming to a certain thread, in our case, is growing, then you want to scrap faster. So you increase the frequency. If that is then if the rate is lower, then you start decreasing. And that is what they did in their paper, and that is the most efficient way, especially for use of resources. Because if you think, at the moment, we have, just to put a cost to all the scrapping, so an instance, a Docker instance, usually runs and uses all the resources on a 8-core Xeon, more or less what, it doesn't matter the physical one. So on an 8-core, on a 24 gig RAM, and it launches 10 instances within it. So the way the scrapping works is that you can launch multiple instances within the container. So it can do, say, 10. That's more or less the optimal number, because after that the processor starts suffering. And then you can launch multiple containers. So if you want to have 100 scrapping instances, then you can start 10 Docker containers, and each of them running 10 instances within it. So if we run at a frequency of 10, we more or less get a result every 6 seconds. So that's about the cost. So actually, let's see if yes.
And is there anything that 4chan, or do they try and prevent scrapping?
That is also a very good question, and so there are a lot of challenges around that. So as you would expect. First of all, you want to have the least possible footprint when you go and extract data, because you don't want to affect your sources in the first place. Not only, but you also don't want them to incur more cost. Now, what we're talking here about is, say, even if it was 100 instances, or we're talking about a website that generates that number of activities. So they have millions of users at a certain time on the site. So the numbers of us scrapping the website are still not massive to be affecting it. However, that is something to keep in mind, because other communities, our research communities probably are doing the same, so that number can become substantial. The second point is that 4chan, not in our case, but most of other websites will have mechanism for detecting scrapping bots, and because most of the cases they don't want. That is why on all our scrapping instances there is a proxy hopping thing that changes IP often, so that you get a chance. But sometimes we do finish behind trapdoors, and then we present it with a CAPTCHA, and that needs human intervention. Somebody actually needs to go and enter the CAPTCHA a couple of times before it gets blocked, and we get some signals when we say, oh, we're not getting result here anymore, do you want to take a look? But yeah, that's also something to say that oXpath at the end is based on Selenium, which means that what it happens in the background is actually it launches Firefox actually is based on Firefox. Firefox then it uses actually Firefox to navigate to get to the end result, and then scraps that information and then closes Firefox. Now all this happens in the background because it will do it in the X video buffer, so you don't see anything. However, you can configure oXpath to actually see that, and you can see in action opening of the browser, going to the URL, navigation, and then closing down. So, and that is what we use when we want to enter the CAPTCHA. So we actually launch an oXpath instance until it gets to the block point, and then we enter the CAPTCHA manually, and then it follows the navigation. So that's yes.
When you say post are deleted, are they deleted by the person who started the thread, or by the person who made the post?
That is the very good question. So that is actually, it would be good to have the answer. However, we have some ideas of what might happen. The thread initiator cannot delete others' posts. So, I mean, once you put your thread there, you can't even delete your thread, I believe, anymore. The only people that can delete a post is either the person that posted the post, or what they call the janitors in 4chan, which is some moderators. I'm not too sure on what rules the janitors delete posts, considering that ideally you should be able to post about anything. However, they have some rules around, mostly say, if you're posting on the political board something that is not political, then they might follow that. In one of our experiments, though, we did that. So it's a different paper, different thing, but we took the deleted posts and then we followed them up with posting them again and see what happens. And they don't get deleted anymore. So it's a bit of a, we don't know yet what is the cause of deletion. Good. So the demos are a bit of let's try and run a few. So the first demo is actually trying to look at if we are connected and everything works fine. We're going to look at a specific stream in Mongo and see the rate of. Oh, sorry, you're not seeing this. I'm not too sure. Maybe I should finish the presentation. see if I can make this as big as possible. So this is it's launching basically, a script that says watcher, but it's looking at a particular collection in Mongo and incoming data, and that is ideally to see the frequency. So this is only looking at the post number, the scrub date, and you can see the frequency of data incoming basically. So if we look at the timing, 27, and so forth. So the instances are actually putting the data into the collection, and then this is just simply watching at what is incoming from the running instances. So that's the scrubbing thing. As another example, I wanted actually to go into one of the Docker instances and look at what the scrapping looks like, which means that this continuous running of oXpath instances and launching Firefox and extracting data, posting it back, and then let me just try and do that. I would have done it actually on the local machine, because that's again Docker, I could launch it, and I was trying that for the demo, and then I was always getting 0 results until I tried to go then manually to 4chan. It says this is completely blocked by your company. You had no chance to get to 4chan. So okay, then we'll try to do this remotely. Can you guys see my password?
Can you make the font bigger?
Sorry?
Can you make the font bigger?
Oh, yes, sorry. Did that help? Okay.
Now we can see the password.
So this is an instance that is just continuously doing that, just running. So you can see the CPU usage is actually quite CPU intensive. That's because of the mechanism of oXpath trying to run and get to the various nodes, and in multiple cases it actually has to follow a certain node because the references are relative, so you get to a certain point and then you follow that to get to the next node, to the next node to follow. And you can see the oXpath working, and in reality you can see the WebDriver, which is part of the Selenium, and then you'll see a lot of Firefox instances running as part of the oXpath. So oXpath will launch the Firefox, will close it down, and then get the data and save it out somewhere. And I think there is also a bit about that's more or less what the topic modeling looks like in R. Actually, it's a two-step process. It's a three-step process. You take the data first of all, and you do some map reduce on it, and let's say I'll skip this, and you get them into a more usable collection, and then once you get there, you start bringing them into R, and you do some more elaboration on the data, because you need to somehow do some sampling. You need to reduce them. We're talking about, say, if I look at the current one of the collections, they are probably, so let's look at this. We're talking about 57 gig of data. So that is, if you think of the frequency that we collecting data with, each of these collections can grow very fast. So we actually do this analysis with having, say, a month of data, and that's already getting us, very big numbers. So if you try to do topic modeling on a 57 gig of data, it's beyond the capacity. So we do some sampling, and then we do all this reduction and getting the data to more usable, and then we output them to some other data set, then that goes into the topic modeling. I've got 1 minute left. We do some more cleaning. We tend to remove actually some of the words that are more meaningless to the topic modeling. and then we build our corpora, we build our document metrics, we build the LDA models, and we also present them using ggplot, and then we build the sentiment analysis model, and then time's up. So I think that if there are any other questions, last questions, good. All right, thank you everyone. Thanks a lot.